All right, welcome to the Silicon Valley Cambridge Exam Hackathon. I'm your lead dev for today, and we're looking at a completely different way to approach Cambridge AS and A-level mathematics. What if we treated paper 9709 not as a traditional boring math test, but as a rigid computer system that we need to hack? I want you to imagine two coders we're monitoring today. First, we have dev Alex. Now, Alex is absolutely brilliant at feeding raw data inputs, but constantly causes massive memory leaks because of poor analysis. And then there's dev Sam. Sam builds beautiful logical loops, but completely crashes the system because they fail the syntax precision rules. Sound familiar? Let's dive into this explainer and learn how to treat these complex, multi-part problems exactly like code, so we can solve them flawlessly.
Okay, system boot sequence initiated. First up, accessing the target mainframe. 2, system architecture and core principles. 3, the method mark algorithm. 4, debugging critical syntax errors. And finally, clearing the examiner firewall. Let's get to work.
Module 1. Accessing the target mainframe, targeting syllabus area 6.2, linear combinations of random variables. Now, you might be thinking, hey, I know the math, I'm good. Well, to clear the examiner firewall, just knowing the math simply isn't enough. It's like having the right password, but typing it into the completely wrong terminal. You must execute precise definitions, establish causal relationships, and most importantly, integrate this topic with other syllabus areas. You can't just compute isolated numbers and hope for the best. You have to write the correct syntax that the Cambridge mainframe is specifically programmed to recognize and reward. This requires serious precision, applying the correct formats, and using the exact appropriate terminology every single time. Module 2. System Architecture and Core Principles. Let's look at the foundational rules of this coding environment. The foundational code rests on understanding expected value, represented as E of aX plus b, and variance. The assessment framework here demands that we don't just, memorize these mathematical formulas like a robot, but actually understand the logical reasoning behind how these variables interact with each other. Deep analytical understanding is prioritized way over a shallow, superficial grasp of the concepts. This is exactly where DevAlex usually causes a system failure. And here is where we map out our pseudocode and really see how different algorithms handle constants. Look, with expected value, the constants map linearly, plain and simple. But with variance, which measures the spread of data, adding a constant b just shifts the data without changing that spread at all, so it drops out completely. But multiplying by a, that actually scales the spread, so a gets squared. If you try to treat these two operations with the exact same logic loop, your system will crash. You absolutely have to structure your reasoning around how these constants actually behave in the real world.
Module 3. The method mark algorithm. This is our master strategy for securing guaranteed marks.
Wait, halt the compile screen for just a second. Before we push this final patch to secure maximum marks and dive into this 5-step algorithm, you need to optimize your system feed. Subscribe to Ace the Exams at Ace the Exams right now and turn on all notifications for weekly system updates. Okay, resuming the compile. By treating a complex math problem like a step-by-step procedural framework, you can systemically farm guaranteed method marks even if your final execution calculation completely fails. Step 1. Deconstruct the prompt. Step 2. Extract the relevant data variables. Step 3. Select your analytical framework. Step 4. Execute with absolutely clear notation. And Step 5. Present it using the correct terminology. If you hit a logic error mid-argument, deploy the Peel syntax structure, point, evidence, explanation link to debug and upgrade your paragraph instantly. Leave out the notation, and the system assumes your code is broken. Your data interpretation skills are essentially your raw inputs. You must accurately extract them from the given texts and tables to ensure your analytical loop functions properly. Without doing this, identifying key elements, applying relevant principles, and verifying your results just becomes impossible. It is literally all about extracting the exact right data to interpret the relationships accurately. Module 4. Debugging critical syntax errors. Let's look directly at the principal examiner reports to identify the top bugs causing point loss. Welcome to the interactive beta testing arena. If we put a 60-second countdown clock on the screen right now, could you locate exactly where a sample student text block fails Cambridge's system standards? We'll look at these 3 highly predictable formatting and contextual errors that cause candidates to drop easy marks. Sometimes students act like dev Alex and hit error number 3, dumping generic formulas without linking them to specific variables in the prompt. Or they might act like dev Sam and hit errors 1 and 2, presenting messy, unformatted work that an examiner simply cannot compile. This system alert straight from the principal examiner proves that generic code simply will not compile. You must bind your mathematical variables to the specific real-world scenario provided. Let's say the question is about the weight of apples and oranges in a shipment, and you just write X and Y without ever defining them as the expected weights of the fruit. You fail the context check entirely.
Module 5. Clearing the examiner firewall. Let's look at the final patch required to elevate your output to a top-tier candidate level. When we compare standard output against top-scoring evaluated output, the difference is night and day. Standard output is superficial and generic. It's just mindlessly repeating what the terminal asked. Top-scoring output, however, questions assumptions, justifies decisions with hard mathematical evidence, and connects to other parts of the syllabus, like the normal distribution. This kind of evaluative thinking, that is your true cheat sheet architecture. To secure maximum marks, your final output string must target the highest cognitive domains. When you evaluate alternatives, justify your final recommendations, or compare different statistical approaches, you prove to the examiner that you don't just know a few lines of code, you know exactly how the entire mathematical architecture functions from top to bottom. So, before your next exam execution run, ask yourself this absolutely critical question. Are you just computing empty data, or are you actively evaluating the context? Make sure you apply the method mark strategy and avoid those critical syntax errors. If you found this breakdown helpful and want to master the cheat sheet architecture, you need to subscribe to AC the Exams at AC the Exams right now. Hit that subscribe button, click the bell icon so you never miss an update, and drop a comment down below with your specific subject and level. Keep compiling, keep testing, and I will see you in the next explainer.